Hello again. So I think we are approaching the correct time. So good morning. This is the second day of AT4 parallel session. Yesterday was a very good day for all the talks that we have received and heard. That was amazing for sure. Today we have 6 talks again, split into 3 parts. Sorry, 3 talks per part. So the first speaker today is Francesco Basha. That if he likes, he can upload his presentation on the screen. I also see Ergali. Ergali is connected.
Yes, I am here.
Oh, okay. You're the second speaker. Well, you will try to upload your presentation immediately after Francesco. So as I will tell you, everybody, please try to stay in 15 minutes if possible, and then you have 5 minutes for any questions. I really hope you will enjoy this parallel session also today. And now it's the turn of Francesco. Please, Francesco, thank you very much.
Thanks, Orlando. So good morning to everyone, and thanks for letting me present my recent work. So today I am going to present a recent work which was recently approved and accepted for publication on JCAP, and it's about the quasi-static approximation in low-density models. So I will first briefly discuss the quasi-static approximation and say a few words about the low-density models, which is the framework where I use this approximation, and then I will discuss 3 different approaches to the quasi-static approximation to show how we can get some of the functions which are also try to be observed via surveys, and then I will compare the analytical results with the full numerical ones. Okay, so we know that the observations are compatible with the lambda CDM model, but this model has problems both on theoretical side and also on data side, as there are some tensions that we can still not explain properly. Therefore, we usually go beyond the lambda CDM models and we investigate models like modified gravity models. And in these ones, the structure formation changes, and therefore the evolution of the potentials and of matter perturbations differs with respect to the lambda CDM. And one of the things that we usually do is to parameterize this different evolution via 2 functions of time, which are usually called mu and eta, which represents the mu, the effective gravitational constant, and eta is the slip, so the difference between the 2 potentials. And to do this, commonly we use the quasi-static approximation. So this is very and widely used in cosmology because it's very simple, but it's a very powerful method because it can give you a quick physical explanation of the physics that we are studying. And the basic idea is that we take differential equations, we get rid of time derivatives in the equations so that only special derivatives are important. And therefore, from differential equations, they become constrained and therefore algebraic equations. And they basically look like a driven harmonic oscillator where the only part that we care at the end is the source term. This approximation is not valid on every scale, but only on scales smaller than the sound horizons. In particular, as you can see here, the scale k must be proportional to 1 over cs, where cs is the sound speed of the model. Now you can see that if the sound speed is very small, then this application is basically useless because we cannot use it at all. There are different formulations on how to use these approximations. All the methods give the same result on small scales by constructions, but they differ on large scales. So the idea is to understand how good they are and why they differ from each other. So I was mentioning that there are a few parameters. So they are all introduced by modifying Poisson equation. So the usual one that we will consider will be this one, which is the modified Poisson equation, where you see that the Newton constant gets multiplied by a function mu, which depends on time and scale. At the same time, we can also modify the balancing equation where we introduce another function which is called sigma. And then we could parameterize the difference, or better, the ratio between the 2 potentials, which is called eta and the slip. Now, by construction, you see that we have 4 quantities, so mu, mu z, sigma, and eta, but only 2 of them are linearly independent, as you can construct the other 2 once you have 2 of them. So you can get free pairs, and usually the ones that are used are even mu and theta or mu and sigma. Theoretically, it's simpler mu and theta, but from an observational point of view, people often use mu and sigma. But here in this talk, I will just limit myself to mu and theta because it's completely equivalent to the other one. So I'm going to apply this formalism to the Ordensky models, which represents the most general theory with second-order equation of motions. It covers really a lot of the models that are studied normally in modified gravity model when there is a single degrees of freedom, a scalar field. And at the perturbations level, we just need 5 functions. One is h, which is the background evolution, or if you want, w, which is the effective equation of state, and then 4 functions which are called alpha, k, b, and t, and they are a linear combination of g functions that you see there before. Now, usually they are unconstrained except for alpha t, which thanks to the gravitational waves is practically 0. So these functions have physical meaning. Alpha k represents the kinetic term, so it's the standard term for quintessence models. Alpha b is responsible for clustering dark energy. Alpha m tells you how much Newton's constant is going to change in time. Alpha t is now 0 and represents deviation from it represents the deviation with respect to the speed of light for gravitational waves, and alpha h, which is usually not used, represents models beyond Ordensky. And then we also have to impose stability conditions because we want that the sound speed is bigger than 0. So this is the framework I want to work on. Okay, so what we usually do is we take the Lagrangian that I showed before, we perturb it, and we write down the field equations, which are the first 4 lines, and the last line is the equation of motion of a scalar field. These functions C are functions of time, and are a complicated function of these alpha functions and h and their derivatives. So to apply the quasi-static approximation, what we do is now to write this in a gauge invariant way. So we combine this equation here with this equation here, and we put this equation here in this one. And then we only consider the terms proportional to k squared. So when we do this, we can then simplify a lot of terms, and the whole system simplifies. And you see that from differential equations, we just have a system of algebraic equations, which we can solve. And once we can solve it, we can get an analytical expression for mu and theta. I'm not going to report the exact expression putting the C functions here because they are rather complicated. But what you can see is that they are proportional to k squared. So they are quadratic because the equations of motions are second order in time and in space. Now, normally you will always see these, and these are because these are the field equations, the ones that we start from. But what you can do is also take the field equations, get rid of the scalar field perturbations, which here is indicated by pi, and you can combine them into the 2 equations for the evolution of the metric potentials. One is the differential equation, which is this one, which tells you the evolution of the scalar field, and the other one is constrained equation, which in GR is simply phi minus psi equals 0, unless you have some anisotropic stress from matters like neutrinos, which would be this term here. But otherwise, we should just be phi minus psi equals 0. Now we do again the same thing. We neglect time derivatives, velocities as well here, matter perturbations in terms of pressure and anisotropic stress, because they are usually negligible at times. And we only consider terms proportional to k squared, which is the scale of interest that we want. So also this one dramatically simplifies. We can solve for the potentials and define mu and theta. And again, we get some expressions which you see are completely different from what we got before. Despite the starting point is basically the same, and the physics which is described is exactly the same as before. There is a third approach that we can use. At the moment, I was just talking of modified gravity, but there is an approach which was developed in Manchester, where I was before, which states that every modified gravity model can be turned into an effective fluid. What does it mean? In general relativity, we write G mu, which is the Einstein tensor, which is equal, besides some proportionality constant, to T mu nu, which is the matter stress energy tensor. If you have a modified gravity model, we can always write the left-hand side as G mu nu plus delta G mu nu, equal always to the matter terms. But of course, we can take the delta G mu nu and bring on the right-hand side, and this I will call it as U mu nu, and this represents an effective dark energy momentum tensor. It's conserved by itself unless we consider interactions between matter and the effective dark energy fluid. And this can be studied using the equation of state formalism, which basically says that also at the perturbation level, we can describe the fluid like at its background level. So at the background, we just need an equation of state, which I call W. So for example, for a lambda CDM, this would be -1. And at linear perturbation, we have two different equations of state. One is gamma and one is pi. Pi is the anisotropic stress, which tells you how different the two potentials are from each other. And gamma is proportional to pressure perturbations. Since we are talking about linear perturbations, they can be written in a linear way, and therefore they are linear combinations of the matter and dark sector perturbations, as you can see here. Now, if we take the continuity equation and the Euler equation for U mu nu, so we start from these ones, which are our equation of state. On small scales, we can neglect velocity perturbations, which is theta. We take the Euler and the continuity equation for the dark fluid, we combine it in a Grove factor-like equation, which looks like this one. So now if you set W to 0, C squared to 0, C pi to 0, and some other terms to 0, then you can just recover an equation which is very similar to the one for the lambda CDM, because in structure they are exactly the same. Now, what we could do is that we always say that in cosmology things slowly vary in time. Therefore, we can consider here as a driven harmonic oscillator, because that's exactly the formulation of this equation. We see that we have a source term which depends on matter perturbations. Therefore, if I neglect this part here, I will have an attractor solution which relates dark sector perturbations, so modified gravity perturbations, to matter perturbations. And now combining this into the Poisson equations, I can get a relation between the two potentials again, which is this one. And then I can also get a relation which gives me the effective gravitational constant. So you see, now we have again, with respect to before, a third approach, which gives me other functional forms which are different from before. But we started at this from exactly the same physical point of view, and we are describing exactly the same physical system. And here it's an example for the most general model allowed by gravitational waves to show how reliable is the attractor. So the black curve is the numerical solution, and the red one is the analytical one. So you can see that there are a lot of scales and times where it works perfectly, but there are other scales, especially very large scales, which approach the horizon, where this approximation doesn't work well. And therefore, we could expect differences with respect to the full numerical solution. So now here I'm showing a comparison between the analytical solution and the numerical solution. So the numerical solution is given by the black curve here for the same model before. So this is the G effective, and here is the slip. And the other curves represents the blue one starting from the field approach, the red one from the potentials, and the yellow one, orange one from the equation of state approach. So the first thing that you see is that in general, none of the approach reproduces well the full numerical solution. The other one is that the metric potential show divergences, and this is not just for this model, but it's for all the models that I was studying in this work. And this is not only for the effective gravitational constant, but also for the slip. So you see that on small scales, there is a perfect agreement, because all the three sets of equations have exactly the same form if we only consider terms proportional to k squared. But on large scales, where the approximation breaks down, of course, we fail to reproduce the full numerical solution. And also, since the coefficients which enter in the equation are different, it's easy to understand why the three approaches give a different result. So now the question is, I have this analytical prediction, which is very good because it's simple. I can calculate it exactly. It's fast, also if I put it in a code, but how good it is. So here is comparison between the approximate solution to get the CMB power spectrum in the top and the matter power spectrum in the bottom, using these approximate expressions. And I compare this with the full solution given by the Boltzmann codes. So now what you can see is that on small scales, everything works perfectly. And on large scales, by large, I mean in L below 5%, below L equal 5, and for K below a couple of times 10 to the minus 3, 10 to the minus 3, I get about 1% difference. And if I go on even higher scales, the difference between the approximate solution and the full solution keeps growing. Now, it's interesting also to see that there is an additional curve, which you can barely see, which I call QSA infinity, which instead of taking into account the scale dependence, I only consider the small scale limit. And this shows that the dominant terms, so the dominant physics, is the one on the small scales, which from a certain point of view is a very good news, because this is much easier to calculate. It doesn't depend on scale, so equations simplify dramatically, and it's the same for all the three approaches, which means that as things are now, we don't need to care about very large scales, but we can only consider very small scales. And to conclude, so the quasi-static approximation is a powerful tool which we can use to study models beyond the lambda CDM. It's exact for up to corrections of the order 1 over k squared, which means that if you go close to the horizon when the approach fails, the potential approach is affected by pathological divergences, and there is no way for solving it unless eventually you tune your parameters, which means you tune your models. And despite the analytical prediction different from each other, from the exact numerical result on large scales, the agreement with observable is in general pretty good. However, if we want to probe very large scales after Euclid, because Euclid won't be able to probe the scales at which this analytical solution is different from the exact one, we need a better analytical expression, which means to relax some of the assumption of a quasi-static approximation. And I conclude here, and thanks for your attention.
Okay. Thank you very much, Francesco, for your very nice talk. So any questions? It seems no questions at all. I have a curiosity just to ask something very quickly. The RDSK approach could be also matched to several classes of dark energy models.
Yes.
So you didn't specialize to any of these classes, as far as I understood, right?
Okay, no, so let's go to something here. For example, this expression here are fully general. So they work for every dark energy modified gravity model, which can be represented within the Ordensky models. If you then want to specialize to a given model, then of course you need to say which of the G function which G functions you activate and what's their functional forms. But in principle, these expressions are fully general, so they cover all Ordensky models.
No, because I saw also the condition for that you have k larger than more or less 1 over the sound speed, so you cannot take a vanishing sound speed, for example, in your approach.
Well, in principle, you can. It just means that its validity is extremely small.
Okay.
But in principle, it works. If you take, so if the sound speed is exactly 0, k would be infinity, and therefore you cannot apply it. Exactly. Otherwise, you say, well, if it's not exactly 0, it's like 10 to the minus 2, then k must be bigger than, let's say, 100 or something like that.
Okay, I see.
Which, of course, is extremely small, but for scale smaller than that, it's applicable.
I see. Okay, thank you for the explanation, and thank you for your excellent talk. Okay, so now it's the turn of Ergali Kurmanov. If he can manage to upload this presentation to share the screen, please. Okay. So from now, as usual, you have 15 minutes. So thank you, please.
Okay, my topic is effects of non-vanishing dark matter pressures in the Milky Way galaxy. And today, the structure, morphology, and evolution of galaxies are based on two important hypotheses about the formation of galaxies. And the first requirement is presence of supermassive black hole at the center of almost every spiral galaxy. This requirement is needed to explain the powerful X-ray radiation from quizzes and to explain the nature of active galactic nuclei. The second requirement is existence of dark matter halo surrounding every galaxy. The existence of dark matter is confirmed by several independent observations. Also, such observations suggest that dark matter does exist, but its nature and the fundamental properties are still unknown, and no suitable dark matter candidates have been directly detected. And the main purposes of work investigate the properties of dark matter in the Milky Way galaxy, and the main task of work analyze the rotation curves of Milky Way galaxy and investigate the equation of state of dark matter and calculate the speed of sound in the dark matter. And the gravitational fields, field of static and spherical symmetric body written as 1, and where T are theta phi time and spherical coordinates. The metric functions phi and m are determined from Einstein equations. And the hydrostatic equilibrium equations in general relativity written as 3 and 4 equations. And in our work, we assume that dark matter is not pressureless, and it gravitationally forms bound clumps over short time scales, and investigate the heavy model of dark matter with pressure can account for observations. And a non-vanishing dark matter pressure as present in TOV equations of 3-4 equations is possible for the Newtonian gravity when C in formulas 3 and 4 tends to infinity. We obtain the equation for the Newtonian gravity. And in both cases, the interpretation of dark matter with pressure is simple. Globally, the pressure is negligible, but locally its contribution cannot be exactly zero as consequence of interacting dark matter constituents, namely weakly interacting particles can provide a small but non-zero pressure. And we know that the pressure, non-zero pressure is necessary ingredient of TOV equations, since any macroscopic static object with pressure must collapse, since we observe cluster or clumps of dark matter which don't collapse. And we now, in our work, we considered some dark matter density profiles, such as exponential sphere, isothermal Burkett, Inasto, Navarro, Frank White profiles. And all profiles has two free parameter except Inasto profile. The Inasto profile has 3 free parameter. And we focus our attention to Milky Way galaxy, where we have a wide number of observations. And to model rotation curves of Milky Way galaxy, we can use observation data from its core to halo regions. And Also, we consider two cases. The first case, there is a supermassive black hole at the center and the dark matter distribution in the core is negligible. The second case, there is a the clumps or cluster of dark matter whose total mass is approximately equal to that of supermassive black hole, and there is no supermassive black hole. And the case where we can see the presence of supermassive black hole at the center of Milky Way galaxy is shown in the left panel of Figure 1, together with observation data covering from inner parts to halo region. For inner parts, we used exponential sphere profile. For the halo regions used Navarro-Frank-White profile, and some profiles has cusp at the center used only the presence of supermassive black hole at the center of galaxy. And the model parameters have been reproduced using same parameters procedure described in the reference 4. And also we purpose to use for the halo region of the Milky Way galaxy next density profiles, say Nasto, Burkett, isothermal, and to compare with inner parts, we use two exponential sphere profile. And in the table, we presented the main results of feeds for core and halo regions of Milky Way galaxies is given. They are given total mass, scalar radius, and central density, central pressure, delta BIC, delta AIC, and the chi-square. For our purposes, we used widely consolidated Bayesian and Akaike information criterion because the statistical criterion give us more information for about density profiles, maybe, than alone chi-square. And we know, as can be seen from table, the exponential sphere profile for the halo has good feed than other profiles. And we know that the exponential sphere profile is typically used for inner parts of galaxy, but we apply to the halo because it gives a finite mass for dark matter as r tends to infinity, which is a great advantage over the profiles for which mass diverges as r tends to infinity. And the pressure profile for the core bulge, these components of the Milky Way galaxy, is written as 5 formula, and for isothermal profile 6 formula, and the pressure profiles for Burkett and Nasto were obtained numerically. And the dependence of density on radial distance r for different density profiles of the halo is shown in the left panel of Figure 2, while the behaviors of corresponding pressures is shown in the right panel. And notice that the Nasto profile curves is different from other profiles and tends to tend to force power. Also, in the Figure 3 is given the plot, the density and the pressure of dark matter for entire Milky Way galaxy using the exponential sphere profile with pressures given by Formula 5. One can see that the pressure of dark matter correlates with its density profile. And next, the speed of sound associated with the dark matter is 7, and the speed we know that the speed of sound plays a key role in the perturbations theory to explain the formation of structures in the universe. And the speed of sound for the core in the bulge, main bulge or disk, and the halo is obtained from the exponential sphere profile and reads as 8. And the relation between the line velocity and the speed of sound is given by 9 formula. And in the right panel of figure 4 is given the speed of sound for dark matter distribution in the Milky Way galaxy. It's interesting to note that the behavior of speed of sound is similar to rotational curve, because we have the relation between the line velocity and the speed of sound as 9 formula. And as expected, the speed of sound is larger towards galactic center, where pressures are higher. And we considered conclusion. We consider model for dark matter distribution in the Milky Way, where the equation of state has non-vanishing pressures and speed of sound. And for the halo of the galaxy, we considered different possible dark matter profiles, and concluded that an exponential sphere profile provides a good feeder for current observations. And for the core of galaxies, in particular in Milky Way galaxy, we considered two scenarios: one with a supermassive black hole in vacuum, and the other an exponential sphere dark matter profile without supermassive black hole. For other components of galaxy, the exponential sphere profile was also applied. And we solved the equation hydrostatic equilibrium to obtain the relation between density and pressure of dark matter profiles, and then estimate the speed of sound in the dark matter fluids of the galaxy. Thank you for your attention.
Okay, thank you. Ergali. Thank you. Warmly thanks also for being so. Yesterday was worse. Do you hear me?
Now, yes.
Okay. I was telling you, thank you for being so well in time, because yesterday was worse for us. We were late today. We are perfectly in time. So any questions to this very good talk?
You have a question?
Yeah, please.
Why did you use this analytical profile rather than, for example, the best fit that are usually provided for the Milky Way?
We use the exponential sphere profile in the whole of the Milky Way galaxy because the exponential sphere profile has good result, delta big and delta IC. And from other profiles, because the exponential sphere has another profiles diverges as r tends to infinity, because we choose the exponential sphere, the whole parts of the Milky Way galaxy, and the exponential sphere profile for the equation of state has analytically, yes. And there are other profiles, and two isothermal profiles has analytical obtained, but it has bad results for our galaxy. And there are other profiles was obtained numerically.
Okay, thank you.
Any more questions? It seems no. Okay, so I would like to acknowledge again you, Ergali, for your nice talk. Thank you very much. Now is the turn of Cyril Venevi. I don't know if my pronunciation is fine, please.
Yeah, it's good. It's fine.
Okay,
So,
great. It's a French name, right? Or
exactly, yeah.
Okay, sorry. Okay, great.
No worries.
Okay, well, it's your turn. Thank you. Please.
So, hi, Ran. Thank you for attending. So, I'm going to talk about the effect of screening mechanism on black hole binary and spiral waveform. So, we do that in the context of Hondensky theory that are used to explain the accelerated expansion of the universe without the need of a cosmological constant. And the most general scalar tensor theory with second order equation of motion, Lorentz and diffeomorphism invariance. And if we restrict to luminal propagation of gravitational wave, we get such an action for the Hondensky theory. So we have non-minimal coupling between the metric scalar field, and we have those functions G2 and G3 that are arbitrary function of the scalar field and the kinetic term of the scalar field. Of course, we don't observe the scalar field in solar system or pulsar experiment. So theories that are used nowadays, they have what we call the screening mechanism. There are different types of screening mechanism. There's the chameleon screening. They use a potential for the scalar field, camouflage with the square of the kinetic term, and Weinstein screening that uses second derivative for the scalar field with this term. So how does it work in practice, pictorially? So you have a source, solar system, pulsar, black holes that emits a gravitational field and a scalar field, but the scalar field is very close to its background value, phi 0 here, and close to the source inside what we call the screen region, the scalar field does not evolve much, but once it reaches the outside of the region, it starts to evolve non-trivially and create this outward expansion. Of course, this poses the problem that in solar system or in pulsar experiments, it's very hard to test, to observe the scalar field because of this screening mechanism. So one idea was to observe the scalar field in gravitational waves. So how it was done until now is that you have a source, here 2 black holes, for example, that emits a gravitational wave. And since we're in the screening region, it was assumed that the gravitational wave does not emit any scalar field. And once this gravitational wave leaves the screening region, it would enter the cosmological scale, and it would interact with the background scalar field, phi 0 here, that is representing by this evolving color. And this background field would interact with the gravitational wave, changing its polarization or its amplitude before it reaches us, the observer. In our work, in our recent work, we were what is the effect? Because of course the source does not emit a very strong scalar field, but it still emits a scalar field. So our goal was to understand what is actually the effect of this emitted scalar field on the gravitational wave. There are 3 main effects of the scalar field. First, at long range, the scalar field is no more trivial, so we would expect it to have quite a significant effect on the gravitational wave. And also in the source, even though the scalar field is small, it would still affect a bit the gravitational field and also the behavior of the source that would in itself also modify the gravitational wave. So we're interested in those three influence of the scalar field. So how do we calculate that? So let me summarize how it's done in general relativity. So you start with the Einstein's field equation. You do a change of variable where instead of describing the field equation with the metric, you describe it with this h mu, the gravitation that we call the gravitational field. And the field equation we written under this term, they can be written as a wave equation. So you have the D'Alembert operator on flat space on the gravitational field is equal to a stress energy, an effective stress energy tensor that depends on the matter content and the gravitational field itself. So now what you just need to do is integrate it, this stress energy tensor with the retarded integral, and you get the solution. Of course, this is not trivial because your effective stress energy tensor depends itself on the gravitational field, and so you cannot solve this integral exactly. So you need to do, you need to assume that h is small, and then you integrate incrementally. So, and also we do the integral over two different regions: the near zone, which is close to the source, where we have the energy momentum tensor different than zero, and the radiation zone, which is far away from the source. And so I will show now how it's done. So in the near zone, close to the source, we assume that the energy momentum tensor describes a sum of point mass object. So you have the density of the object, the Dirac delta. And so we want to do this integral. So first we assume that h to be small or even zero for the first order, and we only integrate over the energy momentum tensor. And since we're close to the source, we assume that we have instantaneous potential in this case. We don't have a retardation effect. And we get the near zone at leading order, Newtonian order. And if you want to have more precision and go to higher order, you can integrate again the effective stress energy tensor with higher order energy momentum terms. And this time you know the leading order of the gravitational field, so you can also put it in the effective stress energy tensor. And in this case, we stop at this order, post-Newtonian order, and you get usually something of this form. So the metric in the near zone, the gravitational field in the near zone, is equal to U. So this is the Newtonian potential, the integral of the density divided by the distance. And you have post-Newtonian expansion, potentials that involve the velocity, the mass, and they are integrals of those things. I don't write them down here, but they're very known post-Newtonian potentials. So now that we know the metric in the near zone, we can make this retarded integral over the near zone. So we take the effective stress energy tensor with the energy momentum tensor, the near zone gravitational field, and we do this integral. In practice, this is not as straightforward, but we can use several techniques. So first of all, we can neglect terms that decay faster than 1 over r, the distance between the source and the observer, since we're far away. And also using the conservation of the effective stress energy tensor, we can rewrite this retarded integral as a sum of Epstein-Wagoner moments, if you want to look at it in the literature. In the case of the radiation zone, we first need to find the gravitational field in the radiation zone. So you do actually the same integral as before, but instead of assuming a specific distance between the source and observer, you take arbitrary distance and you do this integral to know the gravitational field for arbitrary distances. And once you know this metric using this integral, which you get a result that is very similar to the one before, then you can do the integral over the faraway zone, the radiation zone of the effective stress energy tensor of the gravitational field that we just found. All right, then you're just left to sum those two terms together and you get the gravitational waveform. But first you want to describe this waveform with as least parameter as possible. So we rewrite your whole equation with the relative parameter. So the relative position of the two, in this case, the two black holes, the relative velocity, and also the masses of the black hole. And also in your solution, you would have acceleration term, and you want to get rid of them using the two-body equation of motion, using the geodesic equation. So you get the relative acceleration between the two black holes. It would be a Newtonian force and some post-Newtonian effect from relativistic gravity. Once you sum those two terms together, you change the center, you go to the center of mass frame, replace the acceleration, you get this solution. So you get something that decays as whenever the distance between the source and the observer. Mu is the reduced mass, m1, m2 divided by m1 plus m2. And the polarization is described with the relative velocity, relative position, adds also to the amplitude. And then you can have higher order term, post-Newtonian term, and the convention is to use half increments in the notation. And this is what is called the quadruple formula of the gravitational wave. So how do we add the scalar contribution from here? So as we saw, so we take a Hornetsky model with the luminal propagation of gravitational wave, and we want to implement this screening mechanism. So you have the non-minimal coupling, we add a kinetic term, and this was Brown-Sticker term where you have an arbitrary function of the scalar field and a kinetic term of the scalar field. Then you have those three terms representing the chameleon mechanism, the camouflage mechanism, and the Weinstein. And those delta function here, we only want to have one screening mechanism at a time. So we add those delta function that is equal to 1 when you want this screening mechanism to be active and 0 otherwise. And this parameter alpha is the coupling parameter of the theory. It's the parameter you usually want to constrain, and it has its effect. It will tell you how strong is the screening mechanism at play. So how do we model? So first we can do those nonlinear terms. They don't contribute at long range, so we can assume the theory to be behaving as a Brown-Sticker field. And this is the equation we want to solve because we're far away from the source. So what we receive is something that behaves like a Brown-Sticker field. So for that, we can do a slightly different change of variable, and we get also a wave equation for a gravitational field with an extra term, an extra stress energy tensor term that add the contribution from the scalar field. And the scalar field also behaves with the wave equation where you have a stress energy tensor that depends on the matter, content, the gravitational field, and also the scalar field. In the near zone, we do it a bit differently. Screening mechanisms are used to be hard to deal in post-Newtonian expansion because those mechanisms are non-linear, and post-Newtonian expansion have a tendency to linearize the theory. So usually they are not taken into account and you get wrong prediction. But you can use what is called the scaling method to find an effective field equation in the near zone, where you expand your scalar field around the background phi 0 plus a small contribution alpha cube psi. This q is a real number and it's unique for each screening mechanism. And you choose it such that this parameter stays small in your field equation. And effectively, if you take this parameter to be 0, you recover general relativity. And if you take it to be small but not 0, you get a first order term also, and you get the field equation for this correction to the metric. So, okay, so now to compute the correction from the scalar field. So let's start with the long range effect. So in the near zone, we get exactly the same as in GR. So because we assume fully screened source in this case, so we assume that we recover general relativity because the effect is small, the correction is small, and we get the scalar field to be constant. And we need to solve this equation. So in the near zone, it's the same as general relativity. So we just need to integrate an extra term in the radiation zone. But for that, we need the scalar field in the radiation zone. The scalar field is sourced by the near zone. So in this effective stress energy tensor, you need to integrate this. The scalar field in near zone is 0, is constant, sorry. So you get the derivative does not contribute. And once you find, using a retarded integrals, this scalar field, you can find this term here. So you get something of this form. So the gravitational waveform is of the form of general relativity plus this extra term integration over the radiation zone of the extra contribution to the stress energy tensor with the scalar field in the radiation zone. And if you do the whole calculation, you get something that also decays 1 over r, depends on this omega 0 is this omega function with the scalar field phi 0 inside. And this term appears 3 orders lower than the leading order in general relativity, 3 orders lower than the quadruple formula. Now let's turn to the effect in the screen region. So first look at what is the effect of the scalar field directly on the metric, on the gravitational wave. So this time, maybe I'll mention if we would add the extra contribution here of the scalar field and the metric, we would get the same order here, but it would be attenuated by this parameter alpha q that is small. So it would be smaller than this. That's why we don't take into account the extra contribution from the scalar field. So this time in the near zone, we take into account those terms because we want to have a modification of general relativity in the near zone. And by modifying the metric, of course, we modified the near zone metric. So we get something of this form. As I showed before, you have the metric described by general relativity, post-Newton of general relativity, plus extra terms from the scalar field. So you have a Newtonian order term, and then post-Newtonian order terms. Here, I don't write them how they really look like. They're integrals of the scalar field. And you have this factor alpha q that is small and will attenuate the effect of the scalar field. Because you modified the near zone metric, the integral over the near zone will be affected. So you still get the general relativity result from those terms, but you get an extra contribution when you do the integral of the effective stress energy tensor, where you need to add these guys. And it's interesting, but the extra term on the effective stress energy tensor actually does not contribute to this integral because it's at order alpha q to the square and would be then smaller than this term, and we do not count it. Overall, you get the solution. So I don't write the solution, it's a bit complicated, but overall you get a solution that enters at 2 orders of magnitude lower than general relativity. So, but it's attenuated by this parameter alpha q that is, as we'll see later on, is really small. And finally, the effect of the scalar field on the source of the object. So by modifying the metric, you modify the geodesic equation. So you have those extra terms coming in. And since you modify the metric at Newtonian order, you also modify the equation of motion at Newtonian order. So you have the Newtonian force, but you have this extra force involving the derivative of the scalar field with respect to the distance at the position 1 and 2 of the black hole. And you have post-Newtonian term from general relativity and from this extra scalar field, but not concerned with this here. And if you put that in the final answer, you get an extra term that is at the same order of general relativity, leading term, but you have this attenuating factor. So now, finally, we're wondering, like, what is the effect of this scalar field on our, compared to general relativity, right? And this is model dependent, so we can turn toward the specific case, the cubic Galilean model. So we have this function omega is constant, we call it omega 0. And we have Weinstein screening mechanism like this. To satisfy cosmological observation, we want omega 0 to be roughly 10. This alpha q, we want it to be roughly the Hubble constant. And the Weinstein screening q is equal to -1/2, uniquely defined. So you get a dependence of this form for the long range effect of the scalar field and the short range effect. The long range effect depends on this parameter omega 0, the short range effect alpha q, and it depends on the distance between the two objects of the source differently. Well, how does it look like in practice? So if you take the gravitational wave, the first gravitational wave detected, a hypothetical 2 supermassive black holes that merges, or stellar massive black hole with a supermassive black hole, you get this contribution. So we see that the effect of the scalar field in the source is, as expected, really, really small because this parameter alpha q is really small. But interestingly, for symmetric system, the long range effect of the scalar field is at the percent level compared to general relativity. And in the next generation of detectors, LISA or the Einstein telescope, are expecting to have such a precision around the percent level. So we might see this effect of the long range effect of the scalar field in this case. Thank you.
Wonderful. Thank you very much for your excellent presentation. So any questions to Cyril? If not, I have a couple of questions, if possible.
Yes.
Well, I'm really interested in your topic because it's absolutely related to many aspects of modern cosmology. And first of all, just a curiosity, you quoted the Ornesky theory at the very beginning, then Galilean models and so forth. So what's the nature, in your opinion, of the scalar field that you are looking for? I mean, you are considering the coupling between the curvature and the scalar field using gravitational waves, but as usual, in particle physics, you have some physical meaning related to the scalar field itself. So, for example, you take dark energy to be under the form of a scalar field, but you should say that, okay, that field is a given particle, given expected physical objects, something like that. So in your opinion, which kind of scalar fields are expected in your picture, in your approach? This is just a curiosity because you used the theory with the generic scalar field at the very beginning. So
what you mean, you would say,
think?
like, if I would compare that to typically a quantum field theory with the scalar field, you would want, like, what type of scalar field would that be in a theory like that, if I understand correctly?
Yeah, more or less.
Yeah. So, I mean, usually those scalar fields are really used classically to describe some effective behavior. So it's hard to say exactly, and also what would be the effect of the scalar field on like other particles of the standard model. But typically the last example I showed, the cubic Galilean model, it's used, it's an effective theory coming from massive gravity. So you would have, since you give a mass to the graviton, you would have extra degrees of freedom, and this scalar field represents such an extra degrees of freedom. Yeah, I mean, it's hard to know because they're really used effectively as really staying very classic. So it's
in
hard
principle,
to say.
it could be also a dark energy source, for example.
Yeah.
Okay.
Yeah, it's usually used as a dark energy model.
Okay, I see. And afterwards, you quoted the ppm parameters. You know, they are very, very well fixed to given values that seem to confirm general relativity, at least to a background level, because at weak energy regime of gravitational field, we got some results. So do you think that this approach could be used, I mean, the one employing the gravitational waves could be used also for constraining better the ppm parameters?
So
what's your opinion about? Because you expanded up to U, if I saw correctly.
Yeah.
But in principle, it is possible to go further.
Yes. So
please
actually,
correct me if I'm wrong.
Yeah. So for the ppm parameters, actually, if you look at this paper, if you want, so we calculate actually the ppm parameter, and they are relative to this parameter alpha q, so you could get, in principle, from the ppm parameter or the constraint on the ppm parameter, you get the constraint on this parameter alpha q. Now, usually, it's never at the level that we need. Usually, you get 5 orders of magnitude lower. Like, the constraint is not strong enough to actually probe the needed. Those parameters, they need to have a certain value to explain cosmology. And with the solar system experiment, you can only probe up to a certain level. So in theory you can, and so we looked at it for the pulsar systems typically, where you have the strong field constraint on this ppm parameter. So yeah, but it's not. Yeah, we're not at the level of precision yet to actually
sure
test this theory.
Yeah. I mean for next works, not exactly now. And you quoted that Q equal to -1/2 implies H naught for the Galilean example that you presented. Yeah, and you said that alpha to Q is H naught essentially. So in principle, this could also heal somehow the Hubble tension, or do you think it's out of?
Yeah, it's possible. Yeah, like typically, like this model is derived from the again the massive gravity model. So if you take the limit where the mass of the graviton is small compared to the Planck mass, which is the case, you get something of this form. And this model is used actually also to cure the Hubble tension. I mean, every time you add a dark energy that evolves through a scalar field, you can always cure, let's say, the Hubble tension. But there are too many models for now to really point out which one is the closest for summing the Hubble tension if the tension is verified.
Okay. Thank you very much for your terrific talk. And if no more questions, I think that we can have a break, relax with the coffee. I'm so sorry that the coffee will be a self-coffee, unfortunately, for the lacking of coffee break in in the standard conference as usual that we had, unfortunately. By the way, okay, let's see in 30 minutes from now. So Rome time, 11 o'clock here for the next 3 talks in the second part of the AT4 session. Thank you very much. So see you in 30 minutes. Thank you. Okay, it seems that we are in time. I don't know if everybody of you is connected. We just approached 11 o'clock more or less, just a few minutes before. So now it's the turn of Algis Malibayev. Am I right?
Yes.
Okay, with the pronunciation. Many times I'm scared to be wrong somehow. Sorry for that. By the way, you can share the screen. Okay, I see that you're doing. Great. We see the conclusion. Maybe we should see the beginning.
Okay.
We still see the conclusion. I still see the conclusion. I don't know why. Now I see the beginning. Okay, so I think the same for the others. So, well, I think you can start in a minute, and so I think it's fine that you can start. So please, thank you.
Okay. My name is Malibayev Algis. I'm PhD student in Kazakh National University. My talk on topic quasi-normal modes in the field of dione-like diatonic black hole. I did this work in collaboration with Professor Ivashuk and Professor Boshkaev. I will review the motivation of our work, and then I will review about our problem, about our model of black hole and solution. And then I will talk about quasi-normal modes in the canal approximation. And then I will review the hot conjecture relates the damping rate of quasi-normal modes with Hawking temperature. And then I will talk about results and conclusions. Motivation. We consider it the quasi-normal modes because this problem of finding the frequency of quasi-normal modes is very actual in modern physics. And we consider we obtain the frequency of quasi-normal modes for a massless scalar test field in the A canal approximation, and then we analyze these modes. Then we consider checked our results in the limiting cases corresponds to Schwarzschild and Reisner-Nordstrom in order to be sure that our calculations were correct. Also, we investigated the hot conjecture and its validity, and our results was recently published in European Physical Journal. Quasi-normal modes have been considered first by Vishveshwara, Chandrasekhar, Mashkun, and others scientists. The problem of quasi-normal modes relates with the problem, is closely related with the problem of in quantum mechanics. The first figure shows the problem in quantum mechanics connecting with the scattering of in a potential barrier. And figure 2 shows the the problem in quantum mechanics, which close relates with quasi-normal modes, and this problem is has the bounded states, and usually we use these formulas 1, 2, and 3 in order to calculate quasi-normal modes. From first formula, we see that the oscillations damp, and the oscillation of quasi-normal modes consists of two parts: real part and the imaginary part. The imaginary part is less than 0, formula 2, and we see from formula 3 that the frequency of quasi-normal modes is defined through the potential. And figure 3 shows that oscillations has the damping character. This is our model with two scalar fields and two forms. The expression above shows that our model consists of four parts. This first part is gravitational part, second is a kinetic term of scalar fields, and the third and fourth term is Diane-like terms, where G is metric, phi is the vector of scalar fields, F is the two form, lambda 1 and lambda 2 are dilatonic coupling constants. Then we found the solution of our model, formula number 2. This is the general form, which consists of which has two main parameters, A, mu, and P. Formula 2, they are positive, and the formula function H is the radial function, and the F1 and F2 two forms. The scalar field phi has the form formula number 5. We found the exact solution of these parameters, formula number 5, 6, and 7, which these parameters depends on the coupling constants, dilatonic coupling constants, where Q1 and Q2 are Kähler charges, electric and magnetic respectively. Mu is the extremality parameter. We calculated the scalar curvature, formula number 8. From this formula, we see that scalar curvature equals to 0 when A equals to 0 and A equals to 2. This cases corresponds to Schwarzschild and Reissner-Nordström solutions respectively. Then we transformed our metric to another form, from form number 1 to form number 6, in order to find quasi-normal modes. It would be suitable for us, and we used here the Toto's coordinate, formula number 5. And then we considered the Klein-Gordon equation for our massless scalar field, formula number 1. And after some transformations, we obtained the formula number 4. We see that prime V is the effective potential, which consists of two parts. The first part is the aconal part, is called the potential in the aconal part, and the second is in non-aconal. And we found exact expression for aconal part, formula 5, where L is the multiple number, quantum number. And here we see the plot which show the dependence of reduced aconal part of effective potential depending on radial coordinate and torus coordinate. Then we found the maximum values of the scarves at different values of parameter A. And we built the table. Also, we calculated the position of maximum. Formula number 3 shows the value of this quantity. This is meaning of radial coordinate where the effective potential reach the maximum. It also shows this value relates with the photon sphere. And then we calculated the maximum value of effective potential in the Equivalence approximation, formula 6. And then we calculated the value of frequency of quasi-normal modes, formula 2, which is defined through the maximum value of potential. Here, n is the overtone number of the multiple quantum number. And we took the Taylor series and found the real and imaginary part of this frequency, formula 3 and 4. Then we plotted the dependence of real part of Equivalence, the reduced real part of quasi-normal modes, depending on parameter P at different values of parameter A. And also we plotted the dependence of imaginary part of Equivalence of imaginary part of of quasi-normal modes in the Equivalence approximation. Below we see the formulas for these quantities. Then, in order to make sure that our calculations are correct, we considered the limiting cases corresponding to Schwarzschild and Reissner-Nordstrom black holes. Formula 1 and 2 correspond to Schwarzschild solution. This results is consistent with results obtained by Mashkun. And the formulas 3 and 4 corresponds to the Reissner-Nordstrom black hole, and this results is consistent with the result obtained by Anderson. So we made sure that our calculations were correct. And then we investigated the hot conjecture, which relates the damping rate of quasi-normal modes with Hawking temperature, formula 1, and we obtained the expressions for imaginary part of quasi-normal modes and the expression for Hawking temperature in Equivalence approximation. And we plotted the graphs. We considered the case when parameter A is between 0 and 1. And here we see that this relation at different values of A is less than 1. It means that hot conjecture is satisfied. And from this picture, we found the maximum value of the scarves, and when P tends to infinity, we found the limiting value of this relation. And we built a table. Here this table shows this values. From these values, we see that all maximum values of Hod relation is less than 1. It means that Hod relations is satisfied. And limiting values of this relation are different for different values of parameter A. Then we consider the second case when parameter A is between 1 and 2. Here we see that these relations is satisfied when P is enough small, parameter P is enough small, and we found this critical value of these parameters and build the table. Here we see the table which show the critical values parameter P and corresponding value of charge, and below this critical value of parameter P, the hot conjecture is satisfied above this critical, meaning the hot conjecture is violated. And from formula for charge below, we see that there is restriction for this quantity, which depends on parameter A. Conclusions. We have studied the solutions Klein-Fogg-Gordon equation for our massless test scalar field in the background of our static and spherical symmetric metric by using the variable separation method. We found the potential of our model in acanal approximation and use this in order to calculate these frequencies of the quasi-normal modes in the acanal approximation. We considered two limiting cases, Schwarzschild and Reisner-Nordstrom solutions, to make sure that our calculations are correct. We tested the validity of the hot conjecture for our solution by using quasi-normal frequencies in the acanal approximation with the lowest value of the overtone number when n equals to 1. And also we proved this the satisfaction of Ford relation in the range when parameter A between 0 and 1 analytically, not only numerically, but for the case when A is between 1 and 2, we found that the Ford relation satisfied for ground state when n equals 0 for small enough values of charge and big enough values of multiple number L. Thank you for your attention.
Okay, Algis, thank you so much for your contribution. And is there any question?
I have one.
Please.
What is the hot conjecture?
Algis, you can answer.
The hot conjecture, this is the relation. Hot conjecture relates the damping rate of the of frequencies quasi-normal modes with Hawking temperature. Formula you can see from formula number 1.
Okay, thanks. So the imaginary part should be smaller than the Hawking temperature, right?
Yes, the model of imaginary part it have to be less than Hawking temperature multiplied by P.
Okay, thank you.
But we consider it in the ground state and in acanal approximation. Thank you for question.
Thanks to you.
Any other questions to Algis? It seems no more questions. Thank you for your good talk. You can unshare the screen as you wish. So let's go on with the next speaker.
Good morning.
Atagaria, do I'm right?
Yes, almost.
Okay.
Please let me know when I should start.
Exactly now, if you wish.
Okay then. Okay,
Thank you.
All right then. Thank you. So I'm going to be talking about corrections to the Newtonian potential obtained through the post-Newtonian formalism and a bit more. And I'm going to see what sort of changes come to the Newtonian potential if one generalizes the theory one is using to a modified theory of gravity. So based on that, so the total thing today is going to be divided into an explanation of the equivalence principle and a particular densitized formulation of general relativity, which you probably heard in Cyril's talk. So it's going to be similar to that. And then I'm going to be showing how using that formalism, one can obtain equations of motion of two compact objects, also which is known as the two-body problem. So, and then I'm going to be explaining the more part of the post-Newtonian mechanism, and then I'm going to be showing what is the modification to the equations of motion if one considers a very simple extension to GR, which is a quadratic Ffr gravity model. Okay, so let's talk about the binary problem first. In if one as far as one sees, the moon and the apple still falls at the same rate, and this experiment, if one does in any other part of the universe, one will get similar results. So what it means is that the inertial and the gravitational masses can be cancelled from both sides of the equations of motion you're calculating from a mathematical standpoint, that is. So, so this is a prediction of few of the theories of gravity, and they are also based on the principles to begin with. So, so this particular principle is called the equivalence principle, and they are sort of okay. So, but before that, let's talk about something called as a smoothly varying observable, as in what to look for, as what to connect from the gravitational wave data we are getting to the source that is producing them. Can we connect the properties of the gravitational waves to the properties of the source? So, so all of this melds into each other. So is the equivalence principle only valid in general relativity? Can we have extensions of general relativity that is also in a way as diffeomorphism invariant and as well yields the results of yields the predictions of equivalence principle? So based on that, I can just wrongly, mathematically wrong, but I can use a very naive approximation as input a source term as a delta function as to model two source terms in Ffr theory of gravity with r plus alpha r square. Essentially here alpha is minus, alpha is negative. I mean, there are pathologies with such a model, but I will get to that if anyone has a question regarding that later. So yeah, so this in what you see here is the frequency evolution with respect to time. Well, frequency, a function of frequency, and it has been plotted using the GW 150914 data, and the fit of the plot is the first orange line, and the green line shows the GR fit, general relativistic fit. And then we have alpha as negative 1.67 times 10 raised to 9 meter squared, because alpha has here dimensions of length squared. And so if I remove the legend labels, then one might have difficulty in understanding which theory was which, or which theory predicted, or which theory fitted the data well. So here is a bit of a confusion if someone doesn't know GR and FFR, for example, and just looks at this plot. So, and here the effect of the FFR, or the extension alpha R square, has been grossly exaggerated. I will show the non-exaggerated part now. So the equivalence principle, yeah, as I said, moons and planets and the various things follow the same rate. And as a documented principle, it has existed since around 1500 years through the works of John Philoponus and Galileo and then Newton and then Einstein. So general relativity features like a built-in equivalence principle based on general relativity is based on the equivalence principle. It can be loosely categorized or put in a set and a subset, which is the weak equivalence principle, and then a strong statement, which is the strong equivalence principle, which says that even if you have very compact objects and they are going around each other, then even then, till a very good approximation, the very compact objects around which the gravitational fields are very strong, even then, to a good approximation, you can recover the equivalence principle, as in the frequency evolution will not be, in any frame, will not be affected by the structure, by the presence of higher multipolar structure that is more than or less symmetric than spherical symmetry or dipolar symmetry. All right then. So let's take a look at a black box, or like a block diagram of general relativity. You have the Einstein tensor, which is a very non-linear system of differential equations, partial differential equations of 4 variables, but it's quasi-linear because the second order partial derivatives are linear. And you can obtain solutions. You can obtain homogeneous solutions of Einstein theory, for the example, the Schwarzschild and the Kerr, and electrovacuum solutions like Kerr-Newman. I'm sorry for the siren. Okay, all right then. So we have got the input to the Einstein tensor as the initial geometry, or what we call as the metric ansatz, or what the space-time initially in a particular coordinate should look like. And then we also have initial conditions that needs to be specified because these are differential equations. And then in T mu nu is the matter energy momentum tensor, which is quite simple if it's a black hole involved, but if it's quite difficult if it's a neutron star involved. And the energy momentum tensor can contain, or you can include other fields in T mu nu, which might not be just classical matter, but it could be some other things like scalar fields or vector fields and things like that. So also T mu nu will require initial conditions because again, it's you will have a differential equation which is comes as a conservation law of the energy momentum tensor, which is also true because G mu nu satisfies the conservation law. And hence you obtain an output which the dynamics of the space-time and the dynamics of the fields and particles, anything that's in the space-time, their dynamics are solved for in a very closed form manner. So that's the overall picture of how this thing is going to be tackled. Now the basic statement of general relativity itself is that if I have a trace reversed trace of the Riemann tensor, or which is the trace reversed Ricci tensor, then that trace reversed Ricci tensor is proportional to the classical energy momentum tensor, and this is the statement of mathematical statement of general relativity. However, we want to see how the space-time itself, or the metric, changes with the source itself, or what sort of proper relationship I can get between the metric and the energy momentum tensor, which you properly, if you know that if you expand the Einstein tensor fully in the metric, you will get a chaos. So it looks a bit weird, but it can be simplified. The differential equation systems can be simplified in such a manner that a very intuitive relation can be established between a tensor, which is quantifying the space-time, and the energy momentum tensor. But let's go to Ffr field equation before we go on to that, because Ffr field equations can also be written in a very Einsteinian form, and that is given by the first equation that you see. And the effective energy momentum tensor is higher derivatives, or like of more than second derivatives of the metric tensor, which has been collected and put as a function called f prime. F prime is the Ffr theory's partial Ffr theory's f function with a partial derivative with respect to the Ricci scalar itself. So you get the tensor field equations, which are the first two equations, and then the last equation of this page is a trace of the field equations, which sort of is a massive scalar field equation if you just look at it like in a full manner. And it is also sourced by the trace of the classical energy momentum tensor. So now let's see how to solve a general relativistic sort of differential equation systems. And so I have as my base space a maximally symmetric spacetime, which is isotropic and homogeneous everywhere. If one has such a base space, then I can always, this is a coordinate independent approach, that the Riemann tensor is a direct algebraic, has a direct algebraic relationship with the with just quadratic forms of the metric tensor, and it's just proportional through the proportionality constant of constant curvature. And such a spacetime need not be flat. It can be closed or open. It can also be flat, but yeah, it need not be flat. So let's take the base space and design a tensor that has a Riemann symmetry and is better related to the energy momentum tensor, or whatever energy momentum tensor we collect collectively on the right hand side. All right, so for that, as Cyril mentioned before, that we have a Gothic metric, and that is defined by the square root of the negative the determinant. And so I have the Einstein tensor written in a bit more intuitive form, which is a partial derivative of that Riemann tensor-like term based on a particular gauge, as in partial mu of Gothic mu, G mu nu is called the Donder or the harmonic gauge. And then I have on the right-hand side sort of pseudo energy momentum tensors and boundary terms, which will not affect the equations of motion because of our choice of boundary conditions, and the matter energy momentum tensor itself. So this can be solved for. So I can write the Ffr equations in a similar manner if I know how to transform my tensor into another tensor that has a better or a more intuitive relationship with the right-hand side, where all my energy momentum stuff is clubbed together. So similar to the scalar tensor theories of or Horndeski theories that we saw before, it's called the Nutku gauge, that eta mu nu minus phi square root of minus g in the scalar tensor case of Horndeski's case of Philip. But here it's the same similar thing. F prime r acts as the scalar field, and that is itself used as a conformal transformation. When you do a conformal transformation in vanilla general relativity, one obtains a scalar field itself. But in the presence of higher derivative terms in Ffr theories, such a conformal transformation gets cancelled out with double derivatives of the scalar field itself, which is in the right-hand side. So that gives. So here we can utilize a particular conformal symmetry of Ffr theories, and this turns out to be very useful. So then I have the Ffr field equations themselves, which has just an extra term, which is T mu nu effective, and all of my scalar field and like scalar field dynamics, scalar field tensor field dynamics, and tensor is compactified in T mu nu effective, whereas the tensor field dynamics is just in T mu nu LL, or the Landau-Lifshitz form of the pseudo energy momentum tensor, and the mass classical energy momentum tensor is also there. Okay, then I choose a particular form for the Ffr theory, which is a very simple quadratic deviation, which could be used as a low energy limit for high energy theories of gravity. And so I have F prime R as 1 plus F double prime of 0, as in the evaluated at 0 Ricci scalar, Ricci flat backgrounds. And hence, if I have a Ricci flat background, my conformal factor and my scalar field is just unity. So the post-Newtonian sequence is defined as perturbation about a Minkowski spacetime. When you have a tensor that you can perturb, so and that leads to a wave equation that you can have retarded integrals to solve for. And similarly, I can define a Ricci scalar density compared to the metric density, which is given by the last formula of this page. And yeah, so if one does this and uses a similar expansion about the Minkowski spacetime and uses the Lorentz or the Data-under-Gauge condition, one obtains the field equations, the tensor field equations, given similar to the general relativistic equation plus the effective energy momentum tensor perturbatively written down as the last equation of the page, which is T mu nu effective, where we see there is a non-minimal coupling between the Ricci scalar density and the matter energy momentum tensor. And then we have couplings between the Ricci scalar and the trace of the metric, and then various combinations and so on and so forth. So let's see, we also have a scalar field equation. We have the Klein-Gordon equation. Here we see that the right-hand side, the metric tensor or the Gothic metric is not present, only the scalar field itself is present. So the scalar field is not sourced by the metric field or the metric tensor field. So now post-Newtonian expansions assume weak fields everywhere. So that's not the case though. That's not the case in nature. We have the strong external fields as well. So we need to properly define a scaling where the compactification or the compactness of the object is kept constant. And then if I do that, then I can define a coordinate system which I can use for such strong compact objects as well. This is called the strong field point particle approximation. And here we relate the compactness itself with the post-Newtonian parameter epsilon. How does that work is given by this particular image, where in blue the view is as seen by a compact or scaled coordinate system observer, where the radius of the star is always unity, and the black line outside is the boundary of my or the extent to which I am doing this particular scaling. So we basically patch together two different parts of the space-time, which is asymptotically flat in a global sense. And so the Newtonian dynamical time has a hyperbolic character where for constant s, various the phase of the system remains approximately the same. Okay, and then we have to, since the objects are moving, we have to also consider co-moving frames, that we have to fix a frame to the body of the source. I'm going to skip the words. I'm going to directly go to the image. So what is happening is we have an asymptotically flat spacetime, and then we have a body zone where the scaling is taking place, temporospatial scaling, and then we have O prime and O double prime, which are two co-moving coordinates moving along the two sources. And then we have energy or basically any two vector or any tensor, two tensor, transforming from the body zone to the co-moving frame in the following manner where I've written in the left source, body zone 1 below. So yeah, so that's basically the picture of patching together two spacetimes. And then we have to define four momentum, which is the energy momentum tensor, the S mu part or the time space parts integrated all over the three volume. So, and lambda mu nu is just the energy momentum tensor, classical energy momentum tensor, and in general relativity. and the Landau-Lifshitz tensor, which is going to be the effective part for FFR theories. But if I consider an evolution for the four momentum, I can use Gauss's law and convert the whole form into surface integrals, which does not take the classical matter energy momentum tensor, because the surface where I am enclosing the sources, the source remains well inside the surface of my outer boundary of my body zones. So I only have non-compact fields that are changing the equations of motion. And so I have similarly P equals mv sort of a form if I consider the four momentum's first component, or the zeroth component, as the mass at the leading order. And I have the equations of motion as the velocity velocity evolution, which is given by equation 6, as you see here. And they are again a bunch of surface integrals of whatever you have calculated your lambda as in the post-Newtonian formalism. And so what I obtain for FFR theory, if I include the T mu nu effective tensor, is that I have two kind of potentials appearing at the very short scale, which is competing with the Newtonian potential at the inverse R square order, and competing with the Newtonian potential at the very large distance through the Yukawa potential. And yeah, so, and both these forces are repulsive. So we have a balancing act going on here, and where general relativity is just a section of the whole spacetime. And now if I consider the velocity profile, as in do a first integral of the above equations, of the equations of motion, I obtain a velocity profile, which you see if you put R12, which is the distance between the two sources, as very large, then you can ignore the first two terms of the square bracket, and then one is left with a constant. And then we see that the at a large distance, the velocities can be put as a constant, essentially, which is the initial condition of the velocity itself. So yeah, and yeah, to summarize, we have a new treatment for FFR theories, or it could be generalized theories of gravity, where the parameter of expansion in the Lagrangian combined with the determinant of the metric can be used as an expansion parameter, which will help you solve the system of equations in a post-Newtonian fashion. And most of the nonlinear terms are pushed to the higher PN orders, and another new length scale, inverse length scale comes out, which is inverse length that gamma. Yeah, and the extra misbehaving force is sort of misbehaving at two different length scales, and as in not Newtonian or Einsteinian at all length scales. So yeah, and asymptotic flatness is also maintained. Yeah, okay, and it is possible that the net gravitational force can turn out to be 0. So thank you for your attention. That's all. I'm sorry for overshooting.
Okay, no problem. 5 minutes more, and it's not a big deal. Okay, so any questions? It seems no.
Okay. All right,
Okay.
I'll start the share then.
Yeah, and share, please. Thank you very much for your talk, Soham.
You're welcome.
So we have the last speaker, Hernando Quevedo.
Yeah, I am here.
Hi, Hernando.
Hi, Orlando. How are you?
Fine. We all are waiting for you now.
Oh, thank you. Thank you so
many
much.
reasons. Even because we want to go out.
Okay, I understand.
Just kidding. No, it's not true, obviously. Okay, so please, if you can manage to share your screen.
Yeah, I am having some problems with my webcam, so I will switch it off.
No problem.
Share the screen. Just a minute. It is going.
Take your time. The most important thing that we hear your voice. And
Yeah.
If you were a girl, obviously, we wanted to see also your face.
Okay. Not necessary. Okay, wait a minute. Something is going wrong here. I can't share my screen. Okay. I am sharing it.
I don't know. I don't see anything. Maybe our
It's
friends
coming.
can...
It's coming.
Okay, now it seems that it works.
Okay.
So
Now it should. Okay, can you see my screen?
I see it. Yeah, it seems that it works. It's working quite well.
Okay, more or less.
You can.
Okay. So thank you very much, Orlando.
Start, please.
Yeah, thank you. Thank you, Orlando, for the invitation. Okay. So usually when we talk about alternative cosmologies, we think about alternative theories of gravity. So this is exactly what I am not going to talk about. I am going to talk about a different approach in which I'm going to take general relativity as the theory of gravity, and I will complement it with a different approach, which we call geometro-thermodynamics, or GTD, as we used to call it. So, so the plan of my talk is then as follows. First, I will try to explain very briefly the idea of GTD. It is a very well posed mathematical approach. Then I will introduce the idea of compatibility with space-time, compatibility of GTD with space-time. Oh, I'm sorry. And then I will see this particular case in which combining a particular space-time with GTD, we will obtain the lambda CDM cosmological model. And then I will switch into general cosmological fluids to see how it is possible to explore at the same time the geometric evolution of the universe and also the thermodynamic evolution of that. And I will conclude with some conclusions. So what is the idea here? So I will try to propose a different approach to cosmology in which I will assume certain things. The first one is that GR is the valid theory of gravity. I am not going to change Einstein's theory. I will assume that this theory is the right theory to describe gravity. But then I will assume something different, something which in fact is not the first time that people talk about that. I will assume that our universe is a thermodynamic system, but the different thing I am going to do here is I will assume that it is described by GTD, and also that GR is compatible with GTD, and I will see that just by demanding all these conditions, we will obtain some cosmological models which are compatible with what we know about our universe. So let me try to explain very briefly what's the idea of GTD. So this is a mathematical approach, and the result can be given in the following way. We have some sort of dictionary in which on one side we have Riemannian geometry, on the other side we have equilibrium thermodynamics. If you have a thermodynamic system, then with this formalism we find the corresponding equilibrium space, which we call calligraphic E. Then if in classical thermodynamics, the main idea is to give the fundamental equation for a thermodynamic system. So in our case, once you have the thermodynamic fundamental equation, you can also obtain a metric, which is the metric which is compatible with this equilibrium space. So that this equilibrium space turns out to be a Riemannian manifold, and it describes all the possible equilibrium states of the system. Then, since you have a Riemannian manifold, you can calculate the curvature. The curvature of this manifold is interpreted in GTD as thermodynamic interaction. So for instance, if you have a flat space, equilibrium space, then we say that there is no thermodynamic interaction between the particles of this system. If you have a curvature singularity at the level of the equilibrium space, then we interpret this as a phase transition, because it's exactly the points where classical thermodynamics are not valid, is not valid anymore. So these are the phase transition points, and it's exactly the same what happens at the level of geometry, because if you have curvature singularities, you don't know how to describe this space. So also in thermodynamics, you can introduce the concept of free quasi-static processes that corresponds in this GTD formalism to thermodynamic geodesics on this space, on the equilibrium space. So, and some symmetries which are very important for the development of this formalism are the symmetries related to the properties of thermodynamics. For instance, in thermodynamics, you can use different representations to describe a system. So the physical properties of the system do not depend on the representation you are using. And also, you can use different thermodynamic potentials in order to describe a system. The system doesn't change if you change the thermodynamic potential. At the level of geometry, this is what we interpret as diffeomorphism invariance of this manifold and Legendre invariance of an additional manifold, which we call the phase manifold. So this is the main idea of GTD. Everything can be shown strictly from the mathematical point of view. And so a pictorial representation of GTD is this one. We have two spaces. One space is this calligraphic T, which has 2n+1 dimensions. And inside this big manifold, this big space, calligraphic T, there are many subspaces. For instance, this E here, a second E here, these are equilibrium spaces. And in principle, each one of these equilibrium spaces should describe a particular thermodynamic system. This is the idea. And each thermodynamic system is given by a subspace of this big space, and the dimension of the equilibrium spaces is n, where n represents the number of thermodynamic degrees of freedom of the system. So this big space, the phase space, calligraphic T space, is a curved space, and this makes the exploration, the investigation of this field complicated. So there are only very particular spaces in which the curvature is equal to 0, and they will correspond to very particular, very simple thermodynamic systems which are related to ideal gases. So now from the mathematical point of view, GTD, the idea of GTD is to geometrize thermodynamics in such a way that it is Legendre invariant. Let me remind you what's the idea of Legendre transformations. Let's suppose that you have a system with 2 degrees of freedom, 2 thermodynamic degrees of freedom. That means that you need only 2 extensive variables in order to describe it. In this case, we have entropy and we have volume. And the potential we are using to describe this particular system is U, the internal energy. So this is one potential, but you can apply a partial Legendre transformation in order to find, for instance, a second potential. In this case, it's F, which is the Helmholtz energy. You can also use the enthalpy in this way, which is U plus PV. And this is called this is a second partial Legendre transformation. And you can also apply a total Legendre transformation to obtain the Gibbs potential. So the idea is that you can use either U, the internal energy, the Helmholtz energy, the enthalpy, or the Gibbs potential. It doesn't matter which potential you use in order to describe your system. The properties of the system are independent of the use of the potential. Okay. Now, in order to apply this idea to the formalism of GTD, I'm going to introduce just some notations. any one of these potentials will be described by this capital phi, and that means this capital phi can be either U, F, H, or G, and the extensive variables will be represented by E with an index A. A goes from 1 to n, which means that the number of degrees of freedom of the system is n. And for each extensive variable, remember we have an intensive variables. In this case, the intensive variable related to the entropy is the temperature. The intensive variable related to the volume is the pressure. So these are just notations. This is something we need in order to introduce the formalism. Now let me just go briefly to explain what exactly is what we have in this formalism. So we have a big space, as I mentioned before, which is called the phase space. This is a Riemannian contact manifold. And it is a contact manifold in the sense that if we introduce coordinates here, remember we have n intensive variables, n extensive variables, and 1 potential. So we have 2n plus 1 coordinates, which I'm going to use for this space. So this means that it's an odd dimensional space. And it's very well known that once you have an odd dimensional space, you can introduce something which is called the contact 1 form, which according to the Darboux theorem can be written once I choose the coordinates in this way, can be written in this manner. We will see that this is exactly the first law of thermodynamics. So in this phase space, I will introduce a metric which I will call capital G with indices A, B capital. And so the coordinates in this space are Z with indices A capital. So now, the second component of GTD is the equilibrium space, which is a Riemannian manifold. And for this particular equilibrium space, I am going to use the extensive variables of the system. So in this case, there are entropy, volume, and so on. So here in this equilibrium space, I will have also a metric, which I'm going to call G, small g. And the coordinates are the extensive variables, so that the metric can be written in this way. I should mention that in all the cases we have symmetric metrics in the phase space, also in the equilibrium space. And finally, I will introduce the space-time metric, which is, sorry, this is not contact, this is wrong here, just Riemannian manifold. This is the space-time the coordinates I will take just for the case I am going to investigate. The coordinates are t, r, theta, and phi, the polar coordinates, spherical coordinates. So, and the metric in this space-time is written in the standard way. So we have 3 different metrics. Is the capital G, small g for the equilibrium manifold, and small g with a subindex m for the space-time. So these are the 3 spaces I am going to use now. And so the definition I am going to use in order to reach this compatibility I need in my formalism is the following. So we define the equilibrium space as a subspace of the phase space by means of a particular smooth mapping which goes from this equilibrium space to the phase space in such a way that the pullback of the mapping goes to 0. That means that this expression is equal to 0. Remember, this theta was the contact 1 form. So when theta is equal to 0, then we have exactly this relation. This is nothing more than the first law of thermodynamics. So also, once you introduce this particular smooth mapping, you can show that the metric of the equilibrium space is fixed by this map by using the pullback of the map, so that you can calculate the metric of the equilibrium space just by introducing this map. This is also a necessary condition. Once you have this map, then in the equilibrium space is where you have the thermodynamic system. So we demand that this map is also a harmonic map, which means that this particular action, which represents what's called something called the Poliakov action in string theory. Is exactly the same thing. So this action, we vary this action with respect to the coordinates. Then we obtain these particular equations, which means that the Lambertian of all the coordinates of this phase space are equal to 0. The Lambertian is now written explicitly here in this way. So that means that this the equilibrium space is inside the phase space, and also this particular action, its variation is equal to 0, so that I have some sort of field equations for the coordinates of the phase space. So, and these field equations should be satisfied according to my formalism. So one more condition I should apply in order to obtain compatibility is that there exists a map which goes from the space-time to the equilibrium space in such a way that this is also a harmonic map. That means once we write all the action completely and calculate the field equations, that means that the Lambertian of the coordinates of this equilibrium space is also equal to 0. So we have n equations, differential equations here. And so I say that in general, there is a compatibility between space-time and the GTD formalism if, starting from the space-time M, you have a map which goes to the equilibrium space, and from the equilibrium space, you have a second map which goes to the phase space. As for the first map, which goes from the space-time to the equilibrium space, we have these conditions, which means that the coordinates of the equilibrium space must be harmonic functions, and also all the coordinates of the phase space must be harmonic functions. This is the Lambertian of this is equal to 0. So in the particular case we are going to analyze, we have that M is a 4-dimensional. In general, the equilibrium space has n dimensions, and the phase space has 2n+1 dimensions. I am going to use a particular case in which n is equal to 2, and this will give me a particular case, which is cosmology. So, and here I have some very general formulas for the metric of the contact Riemannian manifold, the metric for the equilibrium manifold, and so on. These are just calculations. Let me just show you the particular case I'm going to use in cosmology, which means the following. For the phase space, I will take these coordinates, which are entropy, internal energy, volume, 1/T, temperature, P/T. These are exactly the coordinates we need in order to construct the phase space. So according to that rule of construction of the metric of the phase space is given in this way. As you can see, we have only the coordinates here are exactly the thermodynamic variables we use to describe the system. In the equilibrium space, I will use the coordinates u and v, and the potential in this equilibrium space is S, which is the entropy. And so remember the contact form should be 0 on the equilibrium space. That means that this should be satisfied, and this condition should be satisfied. As you can see, this is just the first law of thermodynamics. Once you have this first law of thermodynamics, you can calculate the metric on the equilibrium space, which is given in this way. As you can see, this subscript means the derivative with respect to the coordinate u and v and so on. So you can see here that once you have S, the entropy, as a function of u and v, then you can immediately calculate the metric of the equilibrium space, which describes the physical properties of the system. This is the idea. And also we have here a metric for the space-time, which is just the Friedman, Lemaitre, Robertson, Walker metric. In this case, I have only the case of the flat special manifold. And so the conditions, once we implement the compatibility within GTD and and the spacetimes are the ones I have here. That means that all the coordinates are harmonic functions, and the particular solution of all these equations can be shown to be written in this way, in which the entropy is given as the logarithm of the energy and the logarithms of the volume. So the main thing here is that now the energy and the volume can depend of time, okay? Which this is the exact result of the compatibility and demand between space-time and GTD. So let's go to cosmology. We know that the field equations, the Einstein field equations for this metric are exactly the Friedman equations. And remember, to construct cosmological model, we have to add some equation of state. Here, instead of using the equation of state, I am going to use what I just got from GTD, which is a fundamental equation. So a fundamental equation which is compatible with this particular space-time. So let's see what we can do with this particular model. So it is very easy to see that in fact we have here a barotropic model in which I have two constants, C1 and C2. If I choose C2 over C1 as 1/3, we obtain a radiation-dominated universe. If I choose C2 equal to 0, then I obtain matter-dominated universe, and C2 over C1 is equal to -1. We have a dark energy. So that means that with this particular, or for these particular cases, we can reproduce what is called the standard cosmological model, the lambda CDM model, because I have all the barotropic fluids, which are the elements of the cosmological model. So, so let's have a look at these barotropic fluids. And the equation of state for a barotropic fluid is this one, P is equal to W times rho. And if we write this from the point of view of GTD, that means in terms of the fundamental equation, then you obtain this very particular and nice differential equation with partial derivatives, and you can just integrate it, and the general solution to this particular equation, differential equation, is this one in which the entropy is just given in terms of any arbitrary function, harmonic function, which depends on V and U in this way. The barotropic factor is given here in this way. So that means that you can use from one side the geometric evolution is given, is determined by the Friedman equations, which are exactly the same we have here. But in the case of our universe, we can take the total density for all the elements of the components of our universe, is the total pressure. So that means that for the particular general fundamental equation for different values of W, we obtain the different types of fluids, barotropic fluids, which are the main ingredients of the cosmological model. So in general, if we want to consider the evolution of the universe of the universe from the geometric point of view, we can use the Friedman equations. And if we want to investigate the evolution from the point of view of thermodynamics, we can choose this very particular fundamental equation in which you can put here all the components of the universe, which means you have here dark matter, you have their energy, barotropic matter, you have radiation, and so on. Whatever you want, you can put it here. You can put all the elements of all the ingredients of the cosmological model here. So here we have three different constants, which are called alpha I. These I won't call them parameterization parameters because in fact this can be used as different parameterization we use in cosmology. And F sub I, these are harmonic functions, which are also completely arbitrary. So we have here a lot of arbitrariness, which we can use in order to construct different cosmological models. So to conclude, let me say that if we demand this compatibility between GR and GTD, which means we demand the existence of these very particular mappings, phi sub m, phi sub e, calligraphic e, then by demanding the compatibility, we obtain here a very particular solution to these compatibility conditions. In this case, I put it a little bit more general solution than the one I was describing before. In this case, this is some sort of generalization of the one I presented before. Here we have some two more constants, alpha and beta, and one can show that with these constants, alpha and beta, one can describe an inflationary model. If we put alpha and beta equal to 0, this is exactly the lambda CDM model I was showing you before. So, and then this particular approach gives us the possibility to investigate from the side of the Friedman equations, the geometric evolution, and from the side of the fundamental biotopic equation, which we get from GTD, you can investigate the thermodynamic evolution. There are many possibilities, remember, because we have a lot of freedom here in these constants and in these arbitrary harmonic functions. So that means that we can construct a lot of different cosmological models. And of course, the simplest one is the lambda CDM we obtain for this particular choice of coordinates and choosing C1 and C2. But in general, there are many, many other possibilities. The main thing here is that we have two possibilities from the point of view of the physics of the model. We can investigate the geometric evolution and also the thermodynamic evolution. The geometric evolution is the GR, the thermodynamic evolution is GTD. So that's it. Thank you very much.
Thank you, Hernando, for your great job presenting your talk. Any questions? It seems no. Just a very quick question. I would like to ask you, in case of non-biotropic fluids, are you able to get some hints about the same thermodynamic expressions that you presented for biotropic ones, or other assumptions should be done?
No. Yes, in fact, if you look at this particular equation I've got here, which I call the fundamental equation of the universe, you have barotropic fluids only if alpha and beta are equal to 0. Once alpha and beta are different from 0, the equation of states are not barotropic. So this is a particular case in which you can analyze a non-barotropic fluids, and in fact, we can use that in order to construct an inflationary model. So non-barotropic equation of states are also allowed here. There is no problem.
When you say non-barotropic, you want to say also that there is a heat exchange or shear, something like that, or it's possible to match such approach with, I don't know, scalar fields?
I would say it is possible to match this approach with the scalar field for very particular cases. In fact, we know that once we reproduce a particular inflationary model, so this is effectively equivalent to a particular scalar field. Once you take the standard cosmological model plus inflation with a scalar field.
Okay, thank you very much.
You're welcome. Thank you.
So by today, it seems that we finished.
Sorry, Arlando.
Do you
Excuse
have
me, this is Yuri Dumin. Can I check my presentation tomorrow? I have presentation tomorrow, but I'd like to check that everything looks okay. Can I do it now?
Okay. Sure. I
share the screen?
Fernando to unshare the screen.
Okay.
And then we see if Yuri can share his own, just to have a check.
Okay. Yeah, okay, let me just try. No, so I don't see the option to share the screen. How to do this?
There is a button. Share the screen.
It should be in the.
Yeah.
Wait a moment. Yeah. Okay. Let me check. Okay. Do you see it now?
It's working. It works.
I still don't see anything.
Okay.
I see dark.
You don't see?
Hernando, you see something? Because you said yes.
Yes, I see. You have to double click to enter full screen mode. The point is, okay.
Do you see now?
Okay,
Yes, yes.
okay.
Okay.
Now it seems that I see everything.
No, it's fine.
Okay. Thank you very much.
No problem.
Thank you very much.
You're welcome. Okay, so we will continue tomorrow. Thank you for this amazing day that was exciting as well as yesterday. And thank you to all the speakers in particular, and to all people who were here to hear these very interesting topics. Okay, so have a nice day, you all, and see you tomorrow at AT4 in case you're interested in. Thank you so much. Bye-bye.
Thank you, Orlando, for organizing this early session. Thank you. Bye-bye.
Thank you. Bye-bye. Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye.